switch to this other microphone. Is that, well, still not getting any sound there, are we? Oh, there it is. Okay, beautiful. So Brian, Nikita, can you guys hear me okay?
Yep.
Yes, no, maybe so?
Yeah, I can hear you, Professor.
Well, let's see. I saw Brian. It looked like you said something there, but I didn't hear you.
Can you hear me?
This may require me turning on the projector. I don't really want to do that. I don't want to distract from the board space, but if we just select the rear display. Okay, you guys can hear me all right. That's good. Unfortunately, I'm not hearing you. Could I get either of you to just say something so I can test if we've got audio coming in?
Hello?
Oof. Yeah, unfortunately, nothing there. Is there a place where I can turn you up here? Maybe this. Oh no, it says it's all the way up. Can we try one more time?
Hello?
Still nothing. Select the speaker, same system, speakers, headphones, echo canceling speakerphone. Let me just try to switch to same as system. Okay, could I get you guys to say something just one more time for me? I'm sorry.
Hello? Hello?
Oh, there it is. I heard something. I heard something. It was quiet. One
Can
more.
you hear me?
Yeah, there we go. All right, victory. Okay, and then the last question here, of course, can you see the board?
Yeah.
Beautiful. Oh my goodness, it's working. Technology, not always a giant pain in the ass. That's not my board lights. Where are my board lights? Probably on this thing somewhere. Maybe there. Oh, yeah. Yeah, there we go. All right. We're in business. I snagged some good markers today. So last time we worked a few USUB problems, which hopefully are mostly review type material for you guys. Today, we're going to cover a few things. We're going to cover section 6.1 on areas between curves. And then I think I also want to talk a little bit about, let's see, I think I gave you one other thing in here. Make sure we're covering all the bases. You can get your homework done. All right, where are we? 5, 5, 6, 1, and 6, 5, which is average value. Okay, so 6.1 is technically a section that's covered in Calc 1, and I don't know how many of your Calc 1 classes actually got to it. I know the people who took Calc 1 with me obviously got there. But I think a hasty review is not a bad idea. And the material that we're going to be talking about in section 6.2 and 6.3, which are finding volumes of solids, kind of using geometry tricks, sort of extend the techniques of 6.1. So I think it's a good idea to take a look at some of those problems. And then 6.5 is a notion from statistics. So we've got this idea, you guys know how to average like 5 numbers, right? You add them up and then divide by 5. What if you want to average all the outputs from a function? All right, so you think of a continuous function f on an interval a, b. There's infinitely many numbers on the interval a, b. Every one of those numbers is associated with an output from the function f. What if I want to average all of those outputs? it's a challenge, right? Finding a way to average infinitely many things. We can no longer just say, I'm going to add them up and divide by the number of things. For one, you'd be dividing by infinity, which is a little complicated. The other is that you're summing infinitely many things. So, let's see, can my high-spec camera track you? Can you guys see the board over here where I've written today?
No, we can't see what you've written.
And okay.
We're looking at that.
It would be nice if this was tracked, but there we go. Okay, yeah, so here we are. We're going to do sections 6.1 and 6.5 today. Areas between curves is not tricky. So the big idea here is if you have if you have one function on the interval a, b, and as long as it's piecewise continuous, you can calculate the area bounded by that function in the x-axis just by integrating the function from a to b. If you have a pair of functions, maybe this is brand new. You gotta be shitting. I thought I was stealing the markers, but I guess I was stealing old markers. All right, so if we have a pair of functions, f and they're sufficiently nice on the interval AB. They don't need to be continuous. They certainly don't need to be differentiable, but we would like them to be at least piecewise continuous. That's the usual condition for integrability in a calculus class. Then the question, what's the area bounded between them rather than the area under one of them is a valid question, right? Because these two functions do bound an area. So can I find this area that is bounded between the green function f and the pink function g? Naturally, the answer is yes. The question is how. You can think of it in terms of Riemann sums. So when I want to describe kind of the proto-integral, the thing you're going to integrate, or the thing that you would construct your Riemann sum with, I'll just come in here and draw a little rectangle. I imagine this rectangle as being at an arbitrary x value. I'll just call it x. So this guy's sitting at this arbitrary x value, x here, which means that the point on the curve down here is x comma g of x. And the point on the curve up here where the rectangle touches the green function is x comma f of x. It might seem like a trivial thing to label the point on the curve, but believe it or not, this is going to be very, very useful when we get to section 6.2. So remember, every point on the graph of a function is some number, comma, f of that number, right? Or g of that number. So the y, when you see people writing like y equals f of x on the vertical axis, what they're saying is that the y coordinate of the point on the graph is f of the x coordinate. If you think of having a shitload of these little rectangles in here, you could construct a Riemann sum. The width of each rectangle we'd normally write as delta x, but in the limiting case, we call it dx. The height of each rectangle is the thing that changes here. So the area of the little Riemann rectangle, call it AI. If this was an xi, maybe I'll just call it A, is the height times the width. The height you would get by subtracting the larger y value and the smaller y value, right? If I want to find this vertical distance, I would take the y value here and subtract from it the y value down here. So that height is f of x minus g of x. Actually, I have a plan here. Let's do it like this. I'm going to use a notation like this in the future. So for now, and I'd like to put this in your notes, dA stands for the little differential area, the small area that comes from a small chunk of x. The width of this rectangle, I think of as just being a little dx width. Right? I know this is a slight abuse of notation. If we're being careful, it's deltas and xi's. But this is a common thing. You'll see this sort of approach in your physics classes too. So that width is just dx. So if I want to find the whole area, A, I would integrate dA. You'll see me use this notation, these three dots arranged in a triangle, it means therefore. So therefore, A is the integral of dA. That's just a true statement in terms of symbols and integrals. We would integrate from little a to little b. And dA, by the little kind of Riemann type argument, is f minus g. So this is the integral from a to b of f of x minus g of x dx. And that's your formula, that's your recipe. So if you want to find the area between two curves, as long as both curves give y as a function of x, right, as long as both those curves pass that vertical line test, you can calculate the area between the curves in this fashion. There's one other little catch here. In this picture, I've made some simplifying assumptions. I've assumed that the green function is always above the pink function. And we know that's not the case, right? Many functions are capable of intersecting and swapping places. So kind of the mnemonic that you want to remember this is that you integrate the upper minus the lower from A to B. And really, this is the way I think of it when I go to set up these problems. We can do a quick example. I'll pan the camera over to the other board here after I write the example. Let's find the area between, let's say, f for my upper, right? Let's say f of x equals 5. And g of x equals e to the negative x from x equals 0 to x equals 3. Something you want to get in the habit of here, and this is something I know that we've kind of lost over the pandemic, unfortunately, is drawing these graphs by hand. So I will ask you, as you go through the 6.1 homework problems, the real reason I go back to 6.1 is to get you practice with sketching curves and regions, because that's going to be hugely important in 6.2. 6.2 and 6.2 are finding volumes require you to be comfortable drawing these pictures and then thinking about rotating the regions, which is a little more geometrically complicated. If you look in the Canvas modules, I'll be posting a Desmos link there that has just a shitload of kind of basic graphs, right? Like logarithms, exponentials, trig functions, polynomial power functions. It's really important that you're comfortable with all of those. They're called parent functions usually, and also comfortable with the rules that allow you to shift them around. So we used green for the upper before. For the lower. So f here is the constant function 5. This graph is a horizontal line. G here is e to the negative x, which is a decaying exponential. So these curves look like this. And then I want to find the area bounded between them from 0 to 3. So 0 obviously is here. Here. So that region is this, and I'll just shade it in black. All right, so this is the area we're looking for. And the game is just to integrate the upper function minus the lower function. You don't need to set up the dA thing, right? You can just jump straight to the integral. This would be the integral from the leftmost x value in our region, which is 0, up to the rightmost x value in our region, which is 3, of the upper function f of x, which is 5, minus the lower function g of x, which is e to the negative x dx. And we talked a little bit about u sub last time. Part of this integral does require a small u sub. So who can tell me how to solve it?
Become 5x to 5. And then e to the negative x would become positive. Just be minusing a negative.
Something like that. Yeah, yeah. This sign will flip. So in order to be super verbose about this, because we're still just kind of warming back up. Technically, we could split this up, right? And calculate the antiderivative separately for each. And that's what you're really doing in your head when you find each of those on their own. The integral of 5 dx, the antiderivative of the constant function 5, is definitely 5x. And we evaluate that from 0 to 3. If I'm being careful here, and this is not a tricky u sub, or z sub, I would sub negative x, which would mean dz is negative dx. Also, my bounds need to change. So when x is equal to 0, z is also 0. When x is equal to 3, z would be negative 3. And we can see what that does to this integral. This minus is this minus. Integral now runs from 0 to negative 3. Those are my new bounds, right? Hold lower bound 0, new lower bound 0. Hold upper bound 3, new upper bound negative 3. E to the negative x becomes e to the z, and dx. If you solve this for dx, you'd see dx is negative dz. So I'll just write negative. Be like this. This negative is a multiplicative constant, right? It's like having a factor of -1 inside. You can come out, and that makes us a plus, just like, I'm sorry, I'm so bad at things. Daniel, just like Daniel was saying. And this is still 0 to -3, and then I just have e to the z dz. Antiderivative for e to the z is e to the z. And we evaluate that from 0 to -3.
Why do we have to do u sub for the e to the negative x stuff?
It's a good question. I mean, if you know the antiderivative for e to the negative x off the top of your head, you're welcome to use it. I call these micro u subs, and a little bit later in the course, I will expect you to be able to do these kind of in your head without any computation. The more general result here is that if you're trying to look up an antiderivative for e to the ax, what would would this be? If we ran through the same procedure, if this was z equals ax.
AE to the AX.
Almost. I know it looks like that from this, but what really happened here is we divided over by the -1 here. So if this was dz equals a dx, then 1 over a dz would be equal to dx. So it's going to be 1 over a e to the ax. And then since I'm writing it as an indefinite interval, so plus c. A little later in the course, I'll refer to these, like I said, with micro u subs and the things that you kind of want to be able to do in your head, but just because we're day 2, I figured it doesn't hurt to get the practice. Really, the reason I wanted to write out the u sub is to drive home this whole changing bounds procedure. Well, I will come over here to finish this off. So when I evaluate 5x from 0 to 3, I plug in 3, I get 15. And then I subtract what I get when I plug in 0, that's 0. So that piece just gives me 15. When I evaluate e to the z from -3 to 0, I'll get e to the -3, so plus, this plus is this plus, and then e to the -3 minus e to the 0, which is 1. So 15 plus e to the -3 minus 1, 14 plus e to the negative. Not bad, right? Subtract the upper minus the lower and integrate from a to b. These problems can be complicated in 2 kind of basic ways. I can give you one or both curves that are not functions of x, or I can give you curves that intersect and trade places on the interval a b. Any questions on what we did here or the notation, anything like that?
Question about the one behind you. Were you finding the area of the red or the rectangle?
So dA, this is the area of the rectangle. And then when I integrate the area of the rectangle, that gives me the area of the red.
So that gives you the area of the red.
Right. Yep. So kind of the idea is what the integral does is it adds up infinitely many areas of these rectangles, right? So I imagine there being a little rectangle here, another one here, another one here, another one here, another one here. And when I integrate the area of just this one, we call it an arbitrary rectangle, right? Because this formula works at any x value between a and b.
Okay, I
So
see.
when you integrate, think of the Riemann sum,
I was
right?
thinking of like writing it all out. I was thinking like integral from a to b of f of x plus integral of a to whatever value that it crosses the x-axis of g of x.
There are ways to kind of think of it like that. We could say if I were to integrate just f from a to b, it would give me the area down to here.
And you would minus that.
And then I subtract off the integral of g. And people get a little bit confused about the part that's below the x-axis here for the integral of g, but remember that would be measured as negative. So when you subtract that off, it really would be adding. And that's a perfectly valid way to think about it too. It's a good observation. Any other questions on this one? Or comments? Okay, let's try something slightly harder. Let's people back over. Okay. The classic in the book. Let me modify this just a little. Let's say sine of pi x and g of x equals cos of pi x. And let's go from -1 to positive. So we all know what the graph of sine x and cos x look like. What does the multiplying by pi inside each of these do?
it stretch out with that?
It modifies the period, certainly, right? Like multiplying by a constant inside is a horizontal scaling. It could be a stretch or a compression. How do you calculate the period of a sine or cosine wave?
I know, it would stretch it up and down, right?
You were right the first time. It's a horizontal scaling. Let's do it real quick. So the trick to calculating the period sine AX or cos AX. The symbol that's usually used for the period is T. I'm not sure why. And it's 2 pi over A. So you take the natural period and you divide by A. The idea is that multiplying on the inside by a constant larger than 1 compresses the graph horizontally. It shrinks it down in the horizontal axis. If A were smaller than 1, then dividing by A would be making this larger. So here, sine pi x and cos pi x, the period t is 2 pi over pi, which is 2. So kind of multiplying the trig functions on the inside by pi does this nice thing where it makes all the interesting points, mins, maxes, and x-intercepts, integers, or rational numbers at least. So let's come in here and draw this. We want to go from -1 to 1. So I'm going to give myself that sort of space here. I'll draw the cosine curve first. So we know that cosine kind of begins at the top of his period. All the way up to 2, that way we get a full period of the cosine wave. And we know he needs to come down and then back up, right? So the cosine, if you plug in 0, the cosine of 0 is 0. If I plug in 1 here, what do I get? What is the cosine of pi? -1. -1. So when x is equal to 1, we're down here at -1. And if I were to plug in 2, what do we get? Yeah, the cosine of 2 pi, which is back up to +1. So my cosine wave here, mark off the half periods. Looks like this. And of course it continues like that forever and ever. Amen. And he does the same sort of thing on the other side. So here is G. And then my sine curve, F, same sort of thing, right? It's a sine wave with period 2. So he's going to start at the origin. He is going to come up to a max here. And then he's going to come back to the origin. Let's see. Same sort of business over here. So besides being quite pretty, from -1 to 1, this bounds an area that is a little bit more complicated. Let me just draw that boundary here and this boundary here. The area we're looking for, I'll shade in black. Is this. The catch is that we no longer have a consistent upper and lower function. Right? Sometimes the green is above the purple, sometimes the purple is above the green. We might be able to exploit some symmetry. There are portions of this which are symmetric, like this region here is the same as this region here, but we're chopping off part of that there. We're adding it back in here. So if you want to be very clever with your symmetry, you could say that the black shaded area here, this, and this, is really the same as this and this, right? The missing piece here is the same as the piece we have over here. So first, let me write down our integral, following the rule. The area bounded here, well, before we do that, I would need to know the x-coordinates of these intersection points. If I want to integrate the upper minus the lower, I need to know where the green is the upper and where the pink is the upper. I need to know what are the x values, for example, here and here, that I would use as my bounds for the green minus the pink here. The sort of first step after drawing the graph is to find the intersection points. If I want to find where these curves are equal, I just need to set sine pi x equal to cos pi x. I need to set the two functions equal to one another. And there's several ways to solve this. You could divide both sides by cos pi x and solve tangent pi x is equal to 1. Or you could try to think about your unit circle. There's a handful of ways we could attack this. So this is the same as, I'll do the first one. The same as saying that sine pi x over cos pi x is equal to 1. And that itself is the same as saying that the tangent of pi x is equal to 1. From the picture, you see that one of these solutions is negative and one of them is positive, right? And there's infinitely many, but at least the ones that we're looking for, the ones which are closest to 0, one of these x values is to the right of the origin, one of them is to the left. So can anybody tell me a positive solution to tan pi x equals 1?
2/2.
That would be the coordinate on the unit circle, right? Or the output from sine and cosine themselves, which would do it. But we're looking for the input. So to solve this, think about the equation
Pi over 4.
almost, yeah. So tan theta is equal to 1 if theta is pi over 4, right? That's one of the solutions
That's
here.
when you get on 4.
Good, which has solutions theta equals plus minus pi over 4, right? Those are the sort of first two that, oh, actually negative pi over 4 doesn't work now. Sorry. So there's one solution, theta equals pi over 4. So if tan theta is equal to 1 when theta is pi over 4, that means tan pi x is equal to 1 when pi x is equal to pi over 4. right? We need the inside of the tangent function to be equal to pi over 4. And then dividing both sides by pi, as Daniel said, we get 1/4. So our positive solution over here, this is at 1/4, right? This x value here is 1/4. We also need this negative solution here, and we see, the period is 2, half period is 1, quarter period is 1/2. So this is somewhere between -1/2 and -1. We could take a guess there, or you could think about your unit circle. We add the s back to solution, and we can think about your unit circle. Where else is the tangent function equal to 1?
5 pi over 4.
That would be a positive solution, right? If I wanted to rotate all the way around to here, 5 pi over 4 works, but be mindful, I'm looking for a negative solution. So the 5 pi over 4 would give me like the next intersection point here. I want the one to the left of the origin.
So then it's 3 pi over 4 or 7 pi over 4.
Almost. Remember, we're looking for a negative value.
Yeah, wouldn't those be negative?
Looking for negative angles. Yeah, so you're right that the values on the unit circle, the coordinates on the unit circle are negative at those angles. But what I'm trying to do is find a value for x here, which would be kind of an angle in this picture, or theta here. I would think of it as theta here. I think we all agree that this is the other point on the unit circle where tangent is 1, right? Where both sine and cosine are negative. And the trick is to think of it like this, right? Instead of rotating forwards around, I'm going to rotate backwards to get that. And that'll give me my negative solution. So if I want to get from here over to here, where tangent is again 1, and theta is the smallest negative theta, such that tangent is 1, how far am I rotating?
Pi over 2.
Pi over 2 would be straight down. So this would be negative pi over 2, and I need to go pi over 4 past that. So I'll tell you how I like to do this. You can count by multiples of whatever fraction of pi you want. So here's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. We can do that going backwards too. Negative pi over 4, negative 2 pi over 4, which is negative pi over 2, negative 3 pi over 4. So that's that angle. That makes sense? This counting by multiples of pi over 4, pi over 3, pi over 6 is a great way to get around your unit circle. So the other solution for theta that I'm looking for is negative 3 pi over 4. And this will give me pi x equals negative 3 pi over 4, which when we divide by pi, this means x equals negative 3/4. And we could have guessed that other ways too, right? Like if I'm counting out, here's 1/4, 2/4, or 1/2, 3/4, 4/4, or 1. We could count in steps like that going backwards too. Negative 1/4, negative 1/2, negative 3/4. So those intersection points are negative 3/4 and positive 1/4. Any questions so far? If I was going to attack this directly, the move would be to integrate from -1 to negative 3/4, pink minus green, from negative 3/4 up to positive 1/4, green minus pink, and then from positive 1/4 to positive 1, pink minus green. And I'll write that down, but then we're going to use a symmetry argument to get the answer much faster.
We're allowed to use symmetry in class, right?
Absolutely. You have to tell me, what symmetry you're exploiting. When you can say this is the same as this.
And just write this equals that, that's it.
Yep, and I would make a note that says bisymmetry, right?
Yeah.
I know what your logic is. Yeah, oh yeah. All right, so if I set this up kind of raw without thinking too hard about the symmetry, and mark this was -3/4. I would integrate from -1 to -3/4. My upper there is the pink, which is sine, so sine minus cosine. I x minus cos I x dx, and then add to that this big middle portion, the integral from -3/4 to +1/4, green minus pink, which is cosine minus sine. And then add to that this last little chunk here, which is the integral from 1/4 to 1 of the pink minus the green, which is sine minus cosine again. But I don't want to compute these three integrals. I'm far too lazy for that. I also don't want to work with these nasty bounds as much as I can avoid them. So we're going to make use of the symmetry argument we observed a second ago. That the slice that's missing here is the same as the slice that's present here. And that with this included here, this guy and this guy are the same. So this whole mess can be done as the integral from -3/4 to 1/4 multiplied by 2.
Now we
Everybody
want
see
to
that?
find the area, that little thing.
So let me come back over here so my online people can see as well. The symmetry argument we're going to use. I'm going to take this slice right here, pick it up, and set it down here. This slice fits perfectly in here. Once I do that, observe that this piece and this piece are the same. So if I want the total black shaded area, by moving this over here, I get two pieces that are the same size. So I can calculate one of their areas and double it. I get, instead of 3 integrals, 1 integral. I think the piece that's most convenient to do that with is the -3/4 to 1/4 piece. So this is equal to 2 times the integral from -3/4 to 1/4 of the green, which is cosine pi x, minus the pink, which is sine pi x. And we would say this is right here by symmetry. Okay, so again, what I'm doing is I'm taking this piece and I'm moving it over here, and then noting that the two resulting pieces are the same size. So if I want the total area, I could just calculate this guy and double it, or I could calculate the integral from 1/4 up to this intersection point, which would be 3/4 and double it.
The way, those two little pieces are the same just by eyeballing it, or?
It's the periodicity of the sine and cosine waves that really do it. So if you extend this graph, you'll notice that it's all just a bunch of things shaped like this, mirrored.
Yeah.
And as long as you've got the same distance, horizontal distance here, which is 1/4, same thing here, this is distance 1/4, you're capturing the same area. But yeah, eyeballing it is a fine way to think of it too. Kind of,
There's a question involving symmetry, we'll be able to just see it pretty much.
as long as you sketch the graph reasonably, yeah.
Yeah.
So the big challenge, of course, is sketching a good graph. But yeah, I think anybody given this graph could probably arrive at that statement. So just make sure that you're comfortable graphing the functions. All right, so our symmetry argument allows us to go from doing 3 integrals to 1 integral, which is really nice. The 2 is going to hang out. These are also little micro U subs, right? just like the e to the negative x or e to the ax. Cosine of ax or sine of ax can be computed really simply, rather than working through the details of those little u subs. I'm going to ask you to come up with the general rule. Oh. So think in the same fashion we did for our e to the ax thing up here, right? We got 1 over a e to the ax because we subbed z equals ax. If I wanted to do this integral, same substitution, right? Z equals ax, I would sub for the inside. So dz would be a times dx, which means 1 over a dz would be equal to dx. So if I were to run a little u sub on this, or a little z sub on this, subbing for the inside, I would get a 1 over a times the integral of cosine z dz. Everybody follow that logic? I'll write it out really quick. So I sub z equal to ax, dz equals a dx. And this means that 1 over a dz is dx. So the dx is 1 over a dz. 1 over a would pop out. And what's left is just cos z dz. Antiderivative for cos z dz is sine z, right? So this is going to be 1 over a times the sine of z, which is ax. And the same substitution works here. This would become 1 over a integral sine z dz. What is an antiderivative for sine z dz?
Negative cosine.
Yeah, negative cos z. So this is going to be negative 1 over a cos ax plus c. And these little micro u subs, we do want to get to a place where we can kind of do them in our head. If your differential is just a constant times the old differential, we should be able to see pretty quickly where those go. So from that, we get antiderivative for cos pi x should be 1 over pi times the sine of pi x, or sine pi x over pi. I'll write it as this, so it matches the formula. And then when I subtract the antiderivative for sine pi x, the minus will make positive. This will become plus 1 over pi cos pi x. And we're evaluating from negative 3/4 to positive 1/4. You can also write those antiderivatives by kind of thinking about the chain rule, right? If I differentiate sine pi x, I get pi cos pi x. So if I want an antiderivative for cos pi x, it would be 1 over pi sine pi x. Factor of 1 over pi can come out. Now I plug in my upper bound. I'll have sine of pi over 4 plus cos of pi over 4. And then I subtract what I get when I plug in my lower bound, which is the sine of negative 3 pi over 4. Plus the cos of negative 3 pi over 4. And we should all be experts with the unit circle. This will not be too tough. What is the sine of pi over 4?
2, 2.
Good. And the cos of pi over 4?
Same thing.
Same thing. So this is 2 over pi. Root 2 over 2 plus root 2 over 2 is root 2. The first big parentheses. And then minus What is the sign of negative 3 pi over 4?
Negative root 2.
I gotta think about it a little bit myself. Yeah. And the cosine of negative 3 pi over 4?
Same thing.
Right. So this is negative root 2 over 2 plus negative root 2 over 2, which is negative root 2. That's what. And now when you take root 2 minus negative root 2, you get 2 copies of root 2. So that's going to be 4 root 2 over 5. And that is your recipe. Drawing the graph can be a little bit tricky, and this is a theme you're going to see through the first little part of the course. So you can be practicing graphing. It's very, very important. I promise you, there will be at least one problem, maybe 2 problems on the first exam where I require you to draw some graphs. And even if you're able to set up the integral without the graphs, which is often not the case, without the graphs, you won't be able to get full credit. Right? Usually about a quarter or half of the credit on the problem comes when they sketch the graphs. So please, as you solve the homework problems, draw the graphs by hand. It's very, very important. There's no way to make WebAssign force you to do that. This is one of the ways that kind of online homework really sucks, because it's possible to like click through and plug things in and eventually make WebAssign happy. But if you want to be preparing yourself for the test, please draw the graphs by hand. If you're uncertain, you're having trouble, you can send me a picture of your work, or you can of course bring it to class. I'd be happy to review it with you if you're coming in person. But it is very, very important to get comfy graphing. Any questions on the setup or solution here? Anything from my HyFlex people? You guys following okay?
Yeah.
Why couldn't we, on the other side of the board, the left side, why did we have to do negative 3 pi over 4? Why couldn't we go around the other way? So
Think of the graph here, right? So if we were to go, say, to the first positive solution, the next positive solution, which would be 1, 2, 3, 4, 5 pi over 4, that's going to give me this intersection point.
oh yeah, it's positive.
Right.
Okay.
So what I was looking for here, the kind of way I like to think of it, are the 2 smallest solutions, the 2 solutions closest to 0, because that's what these are. These are the 2 intersection points whose x values are closest to 0, and one is certainly negative, the other is positive. Later, so one of the cool things about Honors Calc 2, we're going to get to talk a little bit about Fourier analysis. And later, the symmetry of the trig functions about the origin will be very important to us when we do that Fourier analysis. It's going to involve a lot of integrals from like negative pi to pi, that sort of thing. Another reason it's nice to kind of get comfy rotating forwards and backwards around the unit circle is thinking about inverse trig functions, right? Like the tangent function, we restrict his domain from negative pi over 2 to positive pi over 2 in order to make him invertible. And if we are looking for values of the inverse tangent function or inverse sine function, that requires us to think about rotating backwards through the unit circle in addition to forwards. If you were feeling very sneaky, I suppose one thing you could do is translate the whole problem to the right. Yeah, because these are periodic, you could just take this whole picture and move it over here. And there would be a, this, and then a sliver here that we could calculate using those as well. Other questions or comments on this guy? So the other way that these things can become more complicated is if your curves are not functions of x, but functions of y, or maybe one could be interpreted both ways. All right, so what if these things don't pass the vertical line test? Then there is no upper and lower necessarily. There's going to be a left and a right. And really all you have to do is turn your head 90 degrees to the side and everything else is the same. In this case, you'll be integrating with respect to y rather than with respect to x. But everything is more or less the same. So maybe I have an f function looking like this. And I don't know, a g function looking like this. And I want to find the area between them over some interval of y values. So I'm looking for this area here. The reason we integrate upper minus lower is because that height is going to be the larger y value minus the smaller y value in the other setting. Here, you would want to subtract the larger x value from the smaller x value, which means you're going to integrate right minus left. If you want to think about a little rectangle in here, you can. I've shaded this in black, so it's going to be a little bit cluttered looking, but you can think of there as being a little Riemann rectangle in here. Now the thickness of this little Riemann rectangle is a dy thickness. It's a small vertical thickness, small change in y. The point over here is, all right, these curves are x equals f of y. So the x coordinate here is f of y and the y coordinate is just y. You think of y as the independent variable. And the point over here would be g of y comma y. So now your kind of length or height, the thing that we were treating as height previously, would be the larger y, x value minus the smaller x value. So your dA is going to be f of y minus g of y times the thickness of the strip, which is dy, which means the integral the integral for the total area would be integrated from this y value up to this y value. I'm going to write it as y equals a to y equals b, just to emphasize that they're y values of dA, which is integral a to b f of y minus g of y dy. In other words, you just integrate the right minus the left. And the integrals are done dy. The bounds need to be y values again. So I'm not sure we're really clear on that.
I don't understand what you're calling dA, not what you're calling the rectangle dy, the width.
So the width of the rectangle, the reason we normally call it dx is because it's a little x width, right? Like the width of the original Riemann rectangle is a horizontal width. So when we talk about a very small change in x, we usually call that delta x, or in the limiting case dx. To get from here, to go through the width of this rectangle, I'm going through a small change in y, right? Like this might be y equals 1, and this might be y equals 1.2. So my little change there is a change in y, and we call that a dy.
What's the dA again?
dA is the little area that I'm going to integrate to find the big area. So dA is the area of the rectangle. And then A is the total area bounded by these functions. Does that feel comfy-ish?
Yeah. I see.
So kind of the idea is we come up with a little differential area and then we integrate that to get the total area. It's kind of a notation thing. It's also kind of a concept thing that will play well when we talk about polynomials. Okay, let's crunch out a quick example of this. I do want to give you guys the tools for average value today as well. Last time I let you go a little bit early. I didn't realize it, but this is a 75-minute class, not a 50-minute class. So instead of getting out at 10:20, we get out at 10:35. So sort of the classic example here is to take a curve. This. And I want to find the area bounded between these. So let me give you something concrete to call them. Let's call this one. All right, this notation. X equals y squared minus 1. So this vertex over here is at -1. And the green curve, they're going to intersect there, would have to be y equals, let's do so one of these gives y as a function of x. The other one gives x as a function of y. And that's one of the kind of standard challenges once you allow me to start working this sideways system. So you have to choose whether you're going to set this up as a dx integral or a dy integral. In other words, you have to choose whether your strip is going to be oriented up and down, which would be a dx integral, or left to right, which would be a dy integral. And the trick to figuring out which one you want to do is to ask, well, which one gives me an easier integral? Which one gives me fewer integrals? If I were to set this up as an upper minus lower thing, to the right of the origin, the green is the upper and the orange is the lower. To the left of the origin, there's neither, right? The orange is playing the role of the upper and the lower, which is a little bit weird. At the very least, it would require two integrals, right? One integral to compute the stuff to the right of the origin, another integral to compute the stuff to the left of the origin. The integral to compute the stuff to the left of the origin would be a little bit weird. You could get there by solving this for y. You're going to have a plus and a minus when you do that. You could take the plus and then use that to calculate this region and then double it, but it's messy. It's very messy. The alternate approach is to set it up as a dy integral, right? To think of it as a right minus left thing instead of an upper minus lower thing. The green curve is always lying to the right of the orange curve. And if I want to do the right minus left thing, that means I have to solve this for x, which is much easier than solving this for y, which is what I would need to do the upper minus lower thing. So first, because of the geometry, right, the reasons that I just described, there is a consistent right minus left. There is not a consistent upper minus lower. We set this up as a dy integral. In other words, we're going to do the right minus left thing instead of the upper minus lower thing. Two things we need to do. I need to solve this for x, and I need to find my intersection points. So first, y equals -x plus 1. If I add the x over here and subtract the y over here, you see this is the same as x equals 1 minus y. So this green curve can be expressed as a function of x, like this. I need my intersection points. These curves never trade space, they don't swap from right and left within this region, but the intersection points are what are going to come in my bounds here, right? I don't know the y value or the x value here. I know the x value here, but I don't necessarily know the y value here yet. And remember that our bounds should be y values. We would want to integrate from the smallest y value anywhere in this region, which is this, up to the largest y value in the region, which is that. So to find those intersection points, I'm going to set this guy equal to this guy. Right, I'll set 1 minus y equal to y squared minus 1. Now I just pulled these curves out of my ass, so these solutions might not be super nice. Let's see what we get. If I bring these terms over here, this is the same as saying 0 is equal to y squared plus y, and then minus 1 is going to be minus 2. And we can see if that factors. Do we have two numbers whose product is -2 and whose sum is +1? -1?
Yeah.
All right, well, we lucked out. So this is y plus 2 times y minus 1, right? Yeah, lovely. All right, so the y values where those curves intersect are y equals -2 and y equals +1. In other words, this y value right here is -2, and this y value right here is +1. And remember, we want to think of our integral as computing a bunch of areas, adding up a bunch of areas of little Riemann rectangles in here. And that rectangle kind of starts out down here and moves through the region up to here. So my area is going to be the integral from the smallest y value in that region to the largest y value in that region of my right curve given as a function of y, which is 1 minus y, minus my left curve given as a function of y, which is y squared minus 1 from d1. Any questions up to the integral? Okay. So this is integral -2 to 1. I'll have -y squared minus y, and then 1 minus -1 is +2. 1. And the antiderivative for which is -1/3 y cubed minus 1 y squared plus 2y. So this is evaluated from -2 up to +1. I'll continue this up here. Evaluating at +1, we get -1/3 minus 1/2 plus 2. And then we will subtract off what we get when we evaluate this at -2. -2 cubed is -8 times -1/3 is +8/3. -2 squared is +4 times -1/2 is -2. And -2 times 2 is just -4. We're a little short on time, so I'm not going to finish this out, but you guys can do the arithmetic. I guess a little note on a test, if you get me here, I'll give you full credit. All right. Now if you're wanting a nice answer, you can certainly cook one up, but I would accept that on the exam.
What if we make a nice answer, we make like a dumb mistake?
That's an interesting question. So my general rule is like arithmetic mistakes, half point. Calc 1 mistake, 1 point, and a Calc 2 mistake is 2 points. So my free response questions are scored out of 10 points. If you make a mistake that's not relevant to the skills of the class, then I'll take off the smallest chunk I can, which is like a half point.
Yeah.
And if you make a Calc 1 mistake, something that is relevant, then that's at least 1 point. And then if there's a Calc 2 mistake, a mistake on something that I'm specifically testing for, then that would be usually 2 out of 10 points off.
Are the tests the same format as
They're going to be a little different because we're doing paper tests in here, but it's the same sort of thing. So it's going to be about a quarter true false, about a quarter multiple choice, and then half true response. I can show you a sample test when we get a little closer. There's one more thing I want to show you guys before I let you go for the day. And this last thing, we can talk about it more on Monday because it does have some cool geometry behind it. But for the purposes of the homework, I just need to show you the formula really. So let me at least do that before I let you go. This is average value section. I apologize. We're going to go just a little bit over time here. We can't go over much because I have a class at home at 11. You know, to average a set of n numbers, well, then y1, y2, up to yn, we compute the sum y1 plus y2 plus all the way out to yn and divide by the number of numbers, which is n. To average a set of all y values of a function, y equals f of x on an interval a, b, we need to be clever. Right, for the reasons we discussed at the start of class, there's infinitely many y values there. I mean, depending on the function, and if the function is a constant function, there's just one y value there, that wouldn't be hard. But for most curves you think of, there's going to be infinitely many distinct y values attained over that interval. If you imagine, I'll tell you what, let me just give you the result here. So the result is this. The notation is f_av for average value of the function f. It's the corresponding notion to add up all of the values is an integral, right? You guys know that this integral symbol is actually the Latin letter s, just stretched out. It stands for the word sum, S-U-M, to add up. So if you want to just add up all of those outputs, that's precisely what the integral does. The equivalent notion of dividing by the number of numbers here is to divide by the length of the interval, which is 1 over b minus a. And since we are a few minutes over, I won't go through the derivation in its entirety, but I will show you here a little picture. you can kind of think about these things in terms of like mass, in terms of weight. The integral from a to b of f is this area. The average value of that function is the unique constant function that bounds the same area. So for this guy, that would be, that's a little too large. Right about there. Something about like that. Maybe the first one was closer. Yeah, it was. The first one was closer. That's okay. So the idea here is that the orange area and the green area are the same. The first one was probably a little bit closer. Yeah, for this picture should be a little larger. It's the unique constant function that bounds the same area from A to B. And there's a way to think of these in terms of trying to balance weights. There's also a really cool connection to the mean value theorem. And I will share that with you next time. But for the purposes of homework, this is what you need. Right? The problems that I put in your current homework set just ask you to compute the average value of this function or that function. So I'm going to leave it here for today. And then next time I'll show you where this formula comes from, kind of connecting back to this guy. Right? You really can set up a Riemann sum for this, which is kind of akin to adding these things up. And then when you introduce your delta x term, you'll have a b minus a over n. Multiplying and dividing by b minus a will give you this downstairs. So it's a pretty neat derivation, and the connection to the mean value theorem is really cool because there's a separate mean value theorem called the mean value theorem for integrals, which will be fun to talk about. But we can't do it today. We're out of time. I got to drive home, or I'm going to be late for my next class. Please be thinking about your honors project topics and your student teaching topics. So if you take a look, I handed out some hard copies of the syllabus. The very first section that's available for student teaching is 6.4, which is the section on work. And that one we're going to get to next week, right? So next Monday and Wednesday, we're going to be talking about volumes. Next Friday, we're going to be talking about work, which is a concept from physics. And that's the first thing that is available to student teach if you wanted to. The next soonest they're listed in order is 7.2 trig integrals. That will be coming up probably the week after that, either late the week after that or early the following week. So be thinking about the topic for your student teaching. Be thinking about the topic for your honors project. We need to have decided on those by the end of next week. Okay. Any questions? If you want to do work, yeah. I think one other person, I'm not sure if she's here right now or not. Sarah mentioned that she might be interested in doing work. But shoot me an email, right? That's the sort of rule. So whoever Canvas messages or emails me first claiming it gets it.
All right.
All right. Any questions from my Zoom people before we close up shop?
You said it's next Friday, right?
Most likely next Friday, maybe the following Monday. All right, then I'm gonna go ahead and end the meeting here. I hope you guys have a lovely rest of your